Hello Math 1324 students, let's begin lesson 11, exponential and logarithmic functions. First, exponential functions, the easier of the two, and let's begin with a review. Exponent rules. Do you recognize these rules? Let's take a little bit bigger fonts so that you can read better. These rules go way back to pre-algebra days, and then you reviewed in elementary algebra, reviewed further in intermediate algebra. So by now, I assume everybody has some proficiency at the very least. Here we go. Let a and b be positive real numbers, and they're going to be the basis. And let x and y be arbitrary real numbers, and they're going to be the exponents, the powers. When x value is 0, a to the 0 power is 1. Not 0, but 1. When x is 1, a to the first power is just a. In other words, if there's nothing there, no exponent, no power, that means 1 is hidden. A to the negative first power, that's defined as 1 over a, the reciprocal. And finally, negative x power, that's 1 over a to the x power. So if you have any negative power, you can push those as the reciprocal of some power function, and vice versa. If you have some power in denominator, you can flip it over to negative power. And this thing works for arbitrary real number x, and that's really tricky issue, to tell the truth. That's actually a definition, but still there's some reasonings, so let's talk about those. Okay, here's a brief review. It's not a foolproof, just some reasoning behind all these logic. What do you mean by a to the nth power? Recall those? It's the repeated multiplication. Starting from 1, the multiplicative identity, multiply a times a times a, and so on, n times. Now, what if n is 0? That means no multiplication of a, so you just have 1. What if n is 1? That means multiply once. One multiplication, so 1 times a, that's a. What if n is negative 1? That means we have to go backward. We have to undo a multiplication, and that's a division. So one division, you get 1 over a. And negative nth power, repeat its division, so 1 over a to the nth power. That's the logic. And that's how we get a to the nth power for whole numbers, for 0 or positive integers, and that's how you get the power for negative integers. Can we extend those to arbitrary real numbers? It's possible, but we don't do that here at this level, so don't worry about it. Okay, next. The second line, a to the x power times a to the y power, we just add up the power. A to the x power divided by a to the y power, we subtract the power. And please note this parallel inverse operation here. Multiplication versus division. Addition versus subtraction. They're inverse. So we have the natural consequence. And here's the third rule. A to the x power to the y power. We multiply the powers 8 times. Here's some reasonings. And we're not going to prove all those here. Here's some reasonings, and consider those as some helper, some indicator, so that you can memorize these formulae better. Okay, a special case when x and y are all whole numbers, 0, 1, 2, 3, and so on, then you can prove like this, through repeated multiplication. Repeated multiplication x times, and then y times, put together we get total x plus y times. So that's a proof for the special case when x and y are whole numbers. Now what if we have subtraction? It's basically division, because x times, and then among those take off y times, so we have total x minus y times left when x is greater, and in y is greater we have the other way around. And finally, the third rule, a to the x power to the y power. In other words, a to the x power is repeated y times, second, third, fourth, total y times. And each a to the x power is a repeated multiplication x times. Another x times, another x times, another x times, and final y x times. So what's the total? Xy times. That's how you get this rule, a to the xy power. And that's the reasoning when x and y are both positive integers, or at least non-negative integers. For negative integers, you have to take those reciprocals, so things will get a little bit tricky, but it's not impossible, and we can consider doing these in STEM algebra, but it's a bit too much here, so let's not worry about those. For rational numbers, it's going to be an optional topic even in STEM algebra, so let's not worry about these. In any case, everybody should be able to use these freely. And then those partial proofs I showed you for special cases when x and y are non-negative integers, use those as kind of helper or indicator that will help you memorizing these formulas. Okay, let's go to the third rule. If you have different bases but same power, you just distribute the power either for multiplication or division. And the reasoning goes kind of like this. Repeated multiplication, ab times ab times ab times and so on and so forth, but the multiplication is commutative, so a first, x times, and then b, x time, and that's how we get a to the x power, b to the x power. Same goes for division. Multiply all those numerators first, and then the denominators, so you have a to the x power over b to the x power. And then repeat those, then even if you have ABC or ABC over D, E, F, G kind of thing, repeat those, then you can easily see that the same power x can be distributed all over. What if x is negative? It's a bit tricky, but by taking the reciprocal you can prove it. And then if it is rational, that's a bit of headache. So we're not going to do that here. Even in STEM algebra, that's going to be an optional topic, but it works out. Now for real numbers, that's really tricky issue, but that's a bit beyond the scope of this course, so let's stop here. So as far as the exponent rules are concerned, here we go, and let's stop there. Okay, the next topic, exponential functions and the natural exponential function. We're going to talk about those in a separate video. For now, let's stop here.